Yes.
Hey.
How you doing?
Oh, pretty good. How are you?
Good. Spot front.
Yeah. Do it.
Are you speaking?
No, I'm not. I'm just troubleshooting. Hi, Henry. Hey.
Hello.
Long time no see.
Hey,
Pretty good.
yeah.
That's pretty cool.
Yeah.
going?
Pretty good. We've had a lot of very cool questions and good presenters. It's been exciting.
What's been the format? It's been reasonably interactive.
It really depended on like who was presenting. So some people were given like a straight lecture, and that was like any questions, and a lot of people were like interrupt me whenever. And
Yeah, I mean, I'd like to be reasonably interactive, so maybe you can lead the way by asking questions.
they ask questions. No one needs to be forced.
Yeah. Last time that didn't happen.
Oh, in the book club?
What's the kind of how many people have kind of the background of like having done the book, you know, or like knowing a bit about it?
Quite a few. I say maybe like 30% at least either have been in the MOOC physically or took it online.
Okay, so having a few examples from actual slides. Okay.
Yeah.
I'm not terribly well prepared, I'm afraid, so
I'm sure it'll be great. Oh, really? That'd be great.
Glamping.
Oh, glamping?
Yes.
Is this like a thing you guys do?
Not normally, but
It sounds like fun. I've never not done.
yeah, this is
I've seen about Rachel being like the woman live.
yeah,
It's all funny. That's really exciting.
yeah.
And she's doing O'Reilly. Oh, you both are doing O'Reilly conference.
We are, and she is keynoting the JupyterCon. And she's actually apply for JupyterCon on later. No, I don't think I'm looking at that. Rachel, this is a program. Keynote JupyterCon.
So O'Reilly reached out to me and asked if they can like stop by and have a little thing during, like, I don't think they're coming today, but maybe they are.
What do they want to do?
They want to just have like a person who will be talking about the AI conference here and the Jupyter in New York. And just, they also have a raffle, like raffling gold ticket, like, yeah, which is a really cool thing.
What happened to last week's ticket?
Last week's.
The one with the reinforcement learning one?
Yeah.
What happened to that ticket?
The ticket?
Yeah, we had a ticket that was not that I noticed.
Oh, I don't know. I actually have not I'm not really involved with like what he was doing. They were like remember O'Reilly lady?
Yep.
So she was doing this raffle for, yes, so like they're gonna put it all together, all of the tickets they'll get, and then they're gonna give some of them. Hi, Hanoi. Did you get my message?
Yeah, I did. Thank you.
Okay.
Yeah.
And also, you know what I was thinking? GitHub. If you'll go on GitHub, his email is there.
Oh, cool.
So you can like literally, I think
Awesome.
I'm actually certain it's there.
Okay, awesome. Thanks. Yeah, I got you.
Does that happen to reach over there so I can get up
Yeah. No.
Yeah, exactly. Yeah, we started it. It's gonna do part-time classes, online classes, It's right by mission.
But yeah, I would say make sure that I've gotten much nicer and much
Oh, you made it work. That's really cool. You need the space here?
No, I just thought I'd try to make this a little less dodgy. What time do we tend to start in practice?
Whenever we're ready, I think most people should be here by now.
Okay.
If you go into
Hi all. I'm Jeremy. Nice to see you. Nice to see a few familiar faces here, and nice to see quite a few unfamiliar faces, maybe more to the point. That is currently looking...
It's a representation.
More attractive people. How many people have like trained a machine learning model of any kind at some point in your life? Yeah, so for pretty much everybody, this is more a case of understanding the notation and jargon and stuff, I guess. Yeah, let's dive in. I'm more interested personally in kind of more of a discussion than a presentation. So yeah, if you've got stuff like examples or thoughts or questions, just jump in. It's probably better to be closer in so we don't have to yell too much. But yeah, all right. So I don't have a fancy presentation or anything, so I'm just going to go through some of my notes, I guess. So yeah, people often ask me what's deep learning, and obviously it's just one way of doing machine learning. Sometimes I get the question, is it an algorithm? I think the answer is probably not. It's probably maybe more a class of algorithms or kind of an overall approach. I think, having, so I presented this deep learning course here at USF, which ended up on the internet as this deep learning MOOC. And we told people that the prerequisites was just a year of coding and high school math, and that was our only prerequisites. In hindsight, I think not teaching some of these ideas about test sets and cross-validation and stuff was challenging to those people who hadn't seen it before. It's kind of one of those kind of practice skills, which I guess you get after a while, and you kind of forget that if you don't have it, then it's actually not that obvious. So particularly for those of you who haven't done much stuff with test sets and validation sets and stuff, you want to ask more questions. I don't know why this thing is clicking. It's not this, is it? Because that's not later on. No.
Yeah.
The book mentions a couple of suggestions for additional readings, which is Kevin Murphy and Chris Bishop's book. They're both great books. They're both kind of dense books, like this one is. They're more Bayesian in tone, I guess, but they're good recommendations. They're great books if you're interested in really getting deep into machine learning fundamentals. So today we're going to be talking about like what is a learning algorithm, and that's kind of helpful, I think, for getting some of the notation and the jargon in place. So then we'll try to apply that particular example being linear regression. We'll be looking at the question of like how is it different to fit the training data versus trying to find something that generalizes to new data. We'll talk about what hyperparameters are. And so I think one of the things I really liked here is this idea of like, well, what is machine learning? It's basically a type of applied statistics, but there's an increased emphasis on the use of computers to estimate functions and a decreased emphasis on proving confidence intervals around these functions. And the reason this is an important thing to mention is that there are still many people, if not most people, particularly in both academia and industry, who are like very experienced statistical practitioners who haven't really made this switch yet. And the difference between like focusing on confidence intervals. So focusing on confidence intervals, often that's more people focused on small data sets. Like you've done some kind of medical experiment or psychology survey, and you know your N, the number of data points is like 50, and you're trying to figure out like did the medication make a difference or not? And it's really important to know, like, if it's only 50 people, how confident we can be with that difference, and to try and kind of decrease those confidence intervals. They try to use as many assumptions as they can, like what's the distribution and stuff like that. And so I still find, you know, speaking to people who, you know, you would think based on their seniority and their professor of something or other, you would expect them to like really understand machine learning, and often it turns out they really understand traditional statistics. And the two overlap surprisingly little. If anything, people who have had lots and lots of background in statistics can sometimes have a trouble making a switch to thinking about the kind of things we're going to talk about today. It's a very different way of thinking about making predictions. We'll be talking about the difference between supervised and unsupervised learning. I will be having some digressions from time to time, including in this case I'll be trying to argue that there really shouldn't be too much of a difference. Ian Goodfellow is a highly trained expert in deep learning, and so where I disagree with him or have a different digression to him, you should probably assume the book's right and I'm crazy, but I will nonetheless add my thoughts. Most importantly, most deep learning algorithms are based on stochastic gradient descent, or SGD. I guess we won't be getting that today, but it's a super important idea. And actually, the free MOOC that I did, we can get to it down course. It's just a battery problem. Course.fast.ai. One of the lessons actually has these there's both an Excel spreadsheet showing exactly how SGD works and like a little animation created in IPython notebook. So like that's a really good way if you're more of a hands-on learner like me. That's a great way to understand SGD. So to build a machine learning algorithm, you're basically putting together a kind of a little melting pot of different pieces. There's going to be an optimization algorithm, a cost function, a model, and a data set. And it's great to be able to recognize how to pull those things apart so that you can then put them back together again in kind of interesting ways. A lot of people tend to assume that the particular combination of things that they've seen is a machine learning algorithm, but actually mixing and matching is really the way to be successful. Okay. I actually think this introduction is pretty important, understanding like what is a machine learning algorithm. So anything that can learn from data is a machine learning algorithm. And so the first one was 1956. A guy called Arthur Samuel got an IBM mainframe to play checkers better than him, and it learned from the data of playing itself at checkers lots and lots of times and figuring out which techniques turned out to work well and which techniques turned out not to work well. So that was the very first, as far as I'm aware, application of machine learning. So it goes back a long way, 1956, many decades ago now. So we can try to add some specific terminology around this. So we can say that a computer learns when it has some experience, which we're going to call E. So experience we would generally think of as data, right? Because data is the way we put that experience into a computer. And that experience shows the experience based on some class of tasks, T. And so we'll talk more about what tasks might be in a moment, but these are the things that led to the experiences, which led to the data. And then there's some performance measure, P, which we're going to talk about what kind of measures they could be. But in general, we say if the performance at tasks in T as measured by performance measure P improves with experience E, then we say that it's a computer which is learning, and therefore we call this some kind of machine learning approach. All right, so the first thing that they do in the book is to give some examples of each of these things, E, T, and P. All right, so the task. So with machine learning, we can tackle tasks that are too difficult to solve with fixed programs. So a fixed program, I'm sure probably all or most of you have done plenty of coding. You generally write, conditionals, loops, and assign things to variables, and you combine these things in various ways to create a fixed program. So what are a couple of reasons that we might not be able to solve a task with a fixed program? Anyone ever come up with an idea of why that might happen? Yeah.
Way too many cases to do much else switches on.
Yeah, it could be it could be something where you don't really know what's going on behind the scenes, and you've just got lots of examples of what's happened, and so you try to create a huge branching version of it, and it's, that would take forever.
You don't know how to solve it yourself.
Yeah. Can you give an example?
You don't know how to put checkers.
Well, that's a great example. Yeah, I think maybe that's why Arthur Samuels did that. But one I like is you want to program something to be able to see. Here's a picture. What's it a picture of? Is it a cat or a dog? How do you do that? It's like, I don't know. I just look at it and I know, right? So, I think in general, either it's something which you can't really know how you do it because it kind of just happens. Or it's kind of too complex to easily write down. And I think in that latter task, something that seems underappreciated is the idea that even if you do know how to write it down, machine learning might be a way to code it up much more quickly. I don't know if you've noticed it recently, there's been lots of examples, particularly of deep learning algorithms, which do things that we totally know how to do, but they're like really complex fluid dynamics thing or really complex physics calculations. And if you chuck it in a deep learning model, it's just way easier than trying to write it down. So the claim here is made that machine learning is also interesting because understanding machine learning entails developing our understanding of the principles that underlie intelligence. Does anybody have a feeling of whether that's something they agree with or disagree with, or why? I suspect it's a reasonably controversial statement, maybe. Please.
Oh, I'm sorry. I was just going to say, we're trying to teach the machine to be just like us, basically, to make, in some cases, be as good as us, and if, so we want it to be as, as smart as us, and so,
So it's kind of a point of view of if we wanted to really be good at learning from examples, that humans are things that learn from examples pretty well. So maybe it's going to help with that. Yeah.
I was just going to say, it almost fits in that category of, here's a thing we don't know how to do. We don't know how to be intelligent. Let's give it a go, but it also, yeah, I think it's definitely overreach to say.
Yeah, I mean, does anybody want to present a, somewhat stronger counterclaim to this idea that machine learning helps us understand intelligence? Does anybody feel it doesn't or wants to try to express that?
Well, I would say that it doesn't, just based on what I've seen, because we don't learn like one thing and that's all we know how to do, right? Like a machine learning algorithm is pretty single focused most of the time, a task T, whereas a person doesn't learn how to identify cats their entire life. That's all they're learning.
Yeah, although maybe that's not a counterpoint. Maybe your argument actually is that we could learn something about intelligence by building machine learning algorithms that are, pretty good at a wide range of things. And in fact, so there are these kind of companies and research groups that are explicitly trying to solve artificial general intelligence. And interestingly, one of the first organizations to do that somewhat effectively was DeepMind, and their approach was to say, let's not figure out how to play one Atari game, let's figure out how to play 100 of them using the same algorithm. So I guess some people are trying to do that. I don't have a strong opinion about this either way, but I do have an opinion about how to get there is I would say rather than trying to build a brain, trying to build AGI as a thing, I guess OpenAI or DeepMind are trying to do, my view is why not try and solve really important problems that are in the world right now, like hunger and water access and medicine. And my view is that has got an even better chance of leading to intelligence, because it's like that's probably how humans ended up getting intelligent, is we actually have to solve these basic problems, right? So if we try and solve the world's problems in data-driven ways, A, we end up solving the world's problems, and B, we might accidentally end up creating something intelligent anyway. So, yeah.
I mean, one problem is we don't, we always, whenever we make something intelligent, we raise the bar and say, oh, that's not intelligent. Right?
Yeah, there's that as well. So it's like this, exactly. So once people start talking about, I'm trying to make something intelligent, you end up in these stupid semantic discussions rather than just did you help feed people or did you help diagnose disease or whatever. So personally, I find this thing about let's try and create AGI both distracting and takes intelligent people, genuinely intelligent people, away from really important world problems. So anyway. All right, so what's a task? We can't describe the learning itself as the task in general. We have to talk about some more specific task. So if you want a robot to be able to walk, then the walking is the task. And I like that they mentioned here that we could program it, right? But to your point, trying to do so is going to involve writing lots and lots of cases of what if it's leaning slightly to the left or to the right, or this joint goes this direction. Or we could instead try to learn to walk. So often you'll find in your work, you're very tempted the first time you see a problem to just try and write the code, to do it step by step. And I would encourage you, every time that happens, try and see if you can do it with machine learning first. And at first it'll take you a lot longer to do it with machine learning, and after a while it'll take you less time. It's interesting how many people I know who want to learn machine learning, nonetheless, every time they find something at work where they have to build something that solves a problem, they always try and write a heuristic. So I guess it's just what we're used to. Okay, so tasks are generally described of how the machine learning system should process an example. So what's an example? It's generally a row in a data set, and each thing in that is a feature. We'll talk more about what features are in a moment, but there's something that's been measured from an object or measured from an action. Here we get to some nomenclature, and how many people have been to a few of these book club meetings before? Not all of you. Okay, so just in case you don't know the nomenclature, when you see something in bold like this, it's referring to a vector, okay? So look out for that bold. This N here is telling you that the vector is that long, okay? So it's in kind of, it literally means an n-dimensional real space, I guess, but you can just think of it as a vector of length n. Okay, so if you've got a vector of length n, then every entry in that, and so we use this subscript now, so notice that this is not bold anymore, so that's a single number. All right, so the single number, which is the ith feature in this vector, is some feature, something we measured. For example, an image contains pixel values. Now, you may be thinking, well, an image actually is, rows by columns by channels. So it's a tensor, or at least a matrix. It's not a vector, but of course, it's helpful to remember that any time you have an n-dimensional tensor or a matrix or whatever, you can always flatten it out, right? So everything we learn about dealing with vectors will generalize to these higher dimensional things. All right, so they have a particular taxonomy in the book of tasks that can be solved with machine learning. Some of it makes perfect sense, some of it's kind of weird to me, so luckily it starts with the bits that make perfect sense. Generally speaking, most people would say that the two key parts of machine learning, at least supervised learning, are classification and regression. So classification basically says, and again, since most of you know machine learning, let's talk about notation as we see it. We're going to produce a function, right? And we're going to produce a function, and then this column here is such that, right? So we're going to produce a function such that we start with some list of numbers, and we turn it into something out of a set of discrete choices. Right. So, for those of you like me that don't really have a math background, I was trained in philosophy. It's really great to make sure you follow along with the notation when you're reading something where you really want to understand the notation. Often you can totally ignore it, but in this case, we're trying to learn how people write down these kinds of problems and solutions. Okay, so we've got some function that takes a bunch of numbers and turns it into a discrete choice. So in this case, we could say that the bunch of numbers that we start with is a vector called x, right? And then we apply to that this function called f, and we're going to get back this discrete choice, and we're going to call that y. So notice that the x is bold because it's a bunch of numbers, and the y is not because it's a single discrete choice, right? So we're assigning an input described by x to a category defined by a numeric code y. In my MOOC, the first thing we learn to do is how to decide whether a picture is a cat or a dog. Cats and dogs are not numeric codes, but we can easily turn them into them by saying, let's create a variable called is it a cat? And that'll be a 1 if it's a cat, and a 0 if it's a dog. And in general, you can always turn a category into a number just by enumerating its possibilities and arbitrarily giving each one a number. So this description is a mathematical description of really any arbitrary classification problem where you're putting something into a single class. Now in practice, the function that you normally produce at least as an intermediate stage, doesn't produce a single number, a single class, but instead it tends to output a probability distribution over classes. So one of the things I found difficult when I first read this book is that it uses very few analogies and examples. So anytime you read a specific mathematical term like probability distribution over classes, if you've got a background such that that immediately means something to you in here, good. If it's not, the thing I find super helpful is to stop reading and try to come up with an actual physical example, right? So a probability distribution of classes means a bunch of numbers between 0 and 1 that add up together to equal 1, and the things that they add up over are all of the possibilities of the thing you're classifying. For example, 0.7 probability of cat, 0.3 probability of dog would be an example of a probability distribution over classes. And so then as you read the rest of that paragraph or chapter or whatever, you can keep reminding yourself of this physical example. And in fact, Richard Feynman, who was one of the greatest physicists of the 20th century, amazing mathematician, said he never thought about equations as equations. He always found some kind of physical analogy that the equation could represent, and he never read the equations that resolved it. He just thought about the implications of the physical analogy. So he described himself as being really bad at math, but he always said that he could find errors in his other professors' equations very quickly because he would see where the analogy broke down. And I think this is particularly helpful in machine learning and probability because it's generally so easy to come up with a specific example. Okay, so maybe a classification class could be object recognition, so that's what we just talked about. All right, so they make the statement here that modern object recognition is best accomplished with deep learning. I don't think that should be controversial anymore. There's lots of competitions about object detection and object recognition, both on Kaggle and elsewhere, and they're always run with deep learning. That doesn't necessarily mean it's the best practical approach to a particular problem. People often make arguments about whether it's explainable enough, or whether it's fast enough, or whether it can handle small enough data quantities well enough. I think the answer to all those things is it's the best at pretty much all of those things, but just the fact that it's the most accurate maybe is not the only thing we care about. So weirdly enough, or maybe it's not weird because the author of the book happened to write a paper about this. So often when you see there's a chapter in which, a paragraph in which the reference is to one of the authors in the book, you might think maybe this is a slightly biased thing. So the idea that classification with missing inputs is like a key different area that deserves to be right at the top of this list is extremely controversial. And in my experience, classification with missing inputs is easy to handle. You either, if it's a category, you just replace the missing input with a category called unknown. That's just another number now. Or if it's a continuous variable, you can replace it with the median or the mean and add an additional column that's 1 if that thing was unknown and 0 otherwise. So anyway, he has this whole suggestion about how to do it. I don't know anybody that does it that way or thinks of this as a totally different area. Regression, on the other hand, is the other key supervised learning area. Anything where you're trying to predict a continuous number rather than a category.
Alice, can I stop and ask about it?
Yeah.
Do you find that successful, replacing with median and mean? Because I would wonder if, I would think we'd want to do something a little more statistically.
Yeah, if you replace it with the median and add an additional column, which is a 1 if it was originally missing or 0 otherwise, then that works great. It depends on the algorithm, right? So when it comes to structured data, generally it's structured data that has missing values, so things like columns of information about customers in a telecommunications company or something. I tend to use random forests for that kind of stuff quite a lot, and the random forest is going to do a great job of, so there are a few possibilities. The missingness either is or isn't semantically important, right? So the fact that it's missing could be totally meaningless, they just never captured that thing for that person, in which case you never need to be able to predict something, the fact that it's missing, in fact, it's going to have the average value because that wasn't important. Sometimes things are missing and it is important. So for example, any time that when somebody's buying a phone, the person doesn't get asked a particular question because their credit score was really good. So now missingness is correlated with something and we care about it. So in that case, and probably the value that's missing won't be the average, but that's fine, right? Because you've got a whole column that says was it missing or not, so it can like split on that if it wants to, and then if it is, it can treat the values in different ways. So yeah, I find it works pretty well. There are clever things you can do. You can replace the missing values with you can have a model, which actually has the thing with some missing values as a dependent variable, and replace the missing values with predictions of the model. That can work pretty well too. Okay, so if we look at the notation here, regression, we've got a function f such that some bunch of numbers goes to some other arbitrary number. Okay, so the only difference here is the thing it's going to is now a single real number, so that's regression. So it could be, predicting somebody's age or weight, or probability they're going to buy a book or whatever. I spent 10 years of my life thinking about this question about insurance pricing, so that's an interesting one to me. I would say that the difference between regression and classification in practice is generally very small. In deep learning, generally all we do is we change our loss function and our activation function. Traditionally, people that used to think of these as being fairly different and have very different techniques, and you often see these like decision trees where people say like which algorithm should you use, and like one of the earliest steps is it classification or regression, the idea being that you would use totally different algorithms. I think that's totally wrong nowadays. Like my two favorite algorithms of like random forests and deep learning both work equally well with regression and classification and require very, very few changes to move from one to the other. So this difference is much less important than it used to be. They've then got a whole bunch, which I rather wish they instead created a category called generative. Now, generative is, was there a hand up there? No. Generative models just refer to times where the target has like lots and lots of values, right? So, for example, it could be I'm trying to translate Russian into English, so my target is all of the words of an English sentence. Or I could be trying to take a black and white photo and make it color, so my target is all of the pixels of the color photo. Or it could be speech generation, so my target is to create a waveform, and so I've got every sample in the waveform. So that's what I would call generative models, and quite a few of these next ones are all generative models. So, and I think in general, tackling generative models, there's a pretty small number of specific techniques that you learn. They all sit on top of the regression and the classification techniques, and then there's just a few little tricks. So anyway, some of the examples they use here is speech recognition. Okay, so you're given samples of a waveform, and you're trying to create a whole sequence of characters. Interestingly, nowadays, speech recognition has now surpassed human performance. Baidu is definitely the world leaders in this area, so check if you're interested in speech recognition, check out Baidu's papers. They, I think over a year ago, were getting better Mandarin and English recognition than native English and Mandarin speakers. So speech recognition is pretty great. On the whole, that hasn't really made its way into products that we have access to, at least in the US right now, but they're coming. Machine translation. So in fact, in the course, we learn to translate, French into English, but it's just a generative model. You've got a bunch of English words, and your target is a bunch of French words. So nowadays, deep learning is by far the state of the art for that as well. Structured output really, again, it's kind of a slightly arbitrary taxonomy. It covers all of the things we've already been talking about pretty much. Pixel-wise segmentation of images is another thing that we recently taught in the course, and basically that's where you're saying, here's a photo, I don't just want to know if it's a cat or a dog, but I want you to like color the cat, color the house windows, color the seat, and so you end up with every pixel has got a color based on what it is. And it turns out that uses, again, standard deep learning neural nets where the input is the original photo and the output is hopefully somebody has gone through and already for a few of these created these segments, basically drawn the colors in the right spots. And there's some pretty big data sets available nowadays. If you're interested in trying it out, you can get hold of something like Coco. It's a pretty good data set. You just download it and put lots of photos with some of these colors will be in the right spots. It's really fun. Yeah, absolutely. So again, we do it in the deep learning course and everything in the deep learning course. When part one, we run it on Amazon, a single Amazon instance, and part two, we encourage people to build a box. But yeah, a GTX 1080, you can buy these things for $500-600, and there's nothing you can't do with them, basically. You often have to take advantage of transfer learning to do it reasonably efficiently, but again, through the course, we do everything with transfer learning.
How long is the usual training time?
It really varies, I'd say around an hour-ish. There is a particular thing which is really great for segmentation called fully convolutional dense net, or known in the paper as the 100-layer tiramisu, which takes a few hours. It's more intense. There's basically nothing I ever have to train more than overnight for anything ever. Yeah, another good example of this kind of stuff is image captioning, which is, again, something which is kind of fun to play with, where literally you just have some images as your input, and your output is people have written like a sentence saying what the image is, and deep learning does a great job of creating those sentences. All right, so they're kind of all over the place here because anomaly detection is not generative. I think there's an argument about whether anomaly detection deserves to be a separate category or not, because clearly you can represent it as a classification problem. So I used to have a medical diagnostic company, and my main interest was anomaly detection. I think it's like the most helpful thing you can do for a doctor is like tell them, is this person sick or not? And so we basically treated like sick as, any medical data looks odd, basically. Really useful for fraud and stuff like that, and credit. So you can often just treat it as a classification problem of like, is anomaly 1 or 0? But there are some different techniques that people use as well. That hasn't been used as widely in deep learning as like pure anomaly detection. But for example, one of the people that just did our course went on to use simple ConvNet for fraud detection and ended up with something which he had a couple of patents for and has been very successful. So there's definitely some examples in industry of it being used. Speech synthesis or synthesis in general is interesting, and speech synthesis one of the most interesting areas. Currently, there's been a couple of really great papers in the last few months showing some very good speech synthesis results with deep learning. The most recent one, as it points out here, there isn't exactly a single correct output in speech synthesis, but the way people are actually doing it is just to ignore that, and you basically say, okay, here was a sentence somebody was saying, that's the input, here's the waveform they created, that's the output, we'll just try and map one to the other. And so that's the way it's being done in practice. Some of the challenges are like trying to make sure that the speech reflects how we would think about like quotation marks or exclamation marks or things in all caps. And the most recent results are actually showing really effective results from that. And I think one of the tricks is just to have a good data set. Imputation of missing values we just talked about. I don't really think that's a different approach. You just use that as a task. Yes.
Question before you move on. You're
Yeah.
talking about the speech generation. Is the most recent one that you're talking about WaveNet, or is there something that's
No, there's been the Tacotron.
Okay.
Yeah. It's very important if you come up with a cool new deep learning thing to give it a wacky name. And or to be from DeepMind.
Is Tacotron from Deep?
Tacotron, I think, was actually from Google Research.
Okay.
I'm just teasing. Like, there's kind of this problem in deep learning at the moment that unless papers come from really famous people in really elite places, people tend to ignore them. So there's a lot of kind of ignored research out there. Yeah.
Was machine translation task as a machine learning sort of problem?
How do you do that?
Yeah, how do you, what is
Yeah.
the most functional one?
Yeah. So our deep learning course actually has 2 lessons that go through that explicitly. And so the short answer, if you don't have 4 hours, is your input is a sentence, your output is a sentence, and your loss function basically is the accuracy of each word in the target sentence. And so you optimize that. It turns out to work really well. There's actually a good brief summary on the blog of Stephen Merity, who just goes by Smerity. If you look up Smerity neural translation, he has a nice blog post that summarizes Google's neural translation system. It's probably at about exactly the right level. It's like it takes you an hour to go through. You understand the basic ideas. So denoising, I guess, used to be a kind of fashionable thing to talk about, and so the idea basically that you can start with like an image that's got a lot of noise for some reason and turn it into an image that's very clean. The reason it was particularly important for a while was for unsupervised learning. That is when you don't necessarily have a task you know what to do, you're just trying to create some features. People used to do these things called denoising autoencoders, where they basically would take pictures, they would add random noise to them, and then try to remove the noise with the model. They don't really get used so much anymore, and so I'm not sure that denoising is an interesting thing in itself. But there's a whole class of interesting generative models you can do in vision, involving like just making pictures better. So you can like turn black and white into color. You can turn low res into high res. That's called super resolution. If you've got things that are like totally missing, you can add them back in. That's called in-painting. So Microsoft has this cool tool which if you take the panorama and you have like black bits around some of the edges, it like literally fills in the black bits with believable image stuff. Like recent versions of Photoshop and some image tools have something where you can like cut, the person you don't like anymore out of your wedding photo, and it'll like fill it in with natural trees and whatever. Okay, so now we're moving into unsupervised, so density estimation or probability mass function estimation. So, all right, so here we're asked to learn, whoopsie daisy, something P model. It takes a bunch of numbers and returns a single number, and that single number is a probability. And so the probability based on a vector x, so that's our bunch of numbers, we can think of as a probability density function or a probability mass function. So you guys have covered that in the probability chapter. The easier one to understand intuitively is a probability mass function. So it's basically what's the probability that that this thing happened. What's the probability it's a cat? What's the probability it's a dog? Something that I find really helpful is I I basically always, like for every discrete version of something like sum or divide or probability mass, there's a continuous version. Like sum is like integral and divide is like derivative, and probability mass is like probability density. These things come up all the time in deep learning. I find I can ignore the continuous versions all the time because like on computers, you always calculate things in a discrete way, sometimes in a fairly precise discrete way, but you always have to discretize things anyway. So I tend to just like imagine, anytime I see an integral sign, I replace it in my head with a sum, you know, and I replace the infinite number of steps with like lots of finite steps. And suddenly everything's like easier for me at least, to understand intuitively. So here I'm going to focus on the probability mass function. So we basically have some data, right? So we've observed some data. So the data might be a sentence, right? So here's some sentence. Now a sentence is of course not in Rn, but we can easily turn it into Rn. We can basically replace every word with a vector, which kind of reflects the meaning of that word. And so now we can basically say, what's the probability that this is an actual English sentence? Right, so that would be like the probability mass function in this particular case. And so, interestingly, the tasks that have already been described above actually require that the learning algorithm kind of implicitly captures the structure, because like if it didn't, then how is it making predictions? So interestingly, generally speaking, I find the best way to create these kind of density estimation or probability mass estimation models is to basically train an algorithm to do something else. And so I'll give you an example. I mentioned before how one task you could try, one probability mass you could try to figure out is the probability that this sentence is a real English sentence. How many of you have heard of or come across Word2Vec before? That's great. So how did they calculate the vectors for Word2Vec? They didn't have a supervised learning task to do. They basically they kind of invented something that they could calculate a probability mass function for. They took hundreds of millions of actual English sentences from their Google Books corpus, and then they made a copy of all of those, so they've now got a duplicate. And in the copy, they replaced the middle word with a random word. And so now they basically created an additional column, which was a 1 if it was the original correct sentence, and a 0 if it wasn't. And so they built a model which was effectively, can you predict which sentences are real and which sentences are fake, right? So in order to figure that out, it basically has to do this probability mass function calculation, and it ends up creating these fantastically useful vectors. So it's like a good example of how you can do this kind of task. Yes?
When Word2Vec was made and they replaced the word with like some other random word, did they do something where they made sure, like for example, the dog was cute and the dog was fluffy, that cute is not being replaced with...
No, they didn't, right? So sometimes they accidentally ended up with a reasonable sentence. But it turns out that deep learning is insanely good at handling noisy labels. And when I say insanely good, a very recent paper, tried taking the MNIST dataset, which are hand-drawn digits, with the actual digit, and it created 100 copies of every row, and on 99 of the copies, it replaced the true answer with a random answer, and then training on that, it's still at 95% accuracy.
Wow.
Yeah. So like when people, like, and this is really important, like when you're doing whatever it is you do at work or research or whatever, people will want, managers love to talk about all the time they want to spend data cleaning, and like a lot of the time that's not useful, right? So I would say like try it with whatever data you've got before you worry about data cleaning. Okay. So then, performance measure, P. So for classification, it's pretty easy to have a performance measure. We can just use accuracy. So the proportion of examples which give a correct output. This may seem like a minor detail, but it's actually quite interesting. You can, of course, take 1 minus that to get the error rate. And the reason this is important is very, very often, even from like really experienced data scientists, tell them that like something went from 99.9% accuracy to 99.95% accuracy, and I'll be like, isn't that great? And they'll be like, 0.05%, who gives a shit? But actually, we've just halved the error rate, right? So if this was something that was trying to find people, with lung cancer, and we've just like half the number of people that die of lung cancer, that's pretty good. So like in my head, anytime I see an accuracy that's over 50, I generally replace it with 1 minus that, because you have something that just intuitively makes a lot more sense. Okay. All right, so now we get to the really important stuff. We really care about, not about just the accuracy on the data we have, but what we really care about is the accuracy on data that we haven't trained with. So we have a test set. And my favorite example of the test set is a cackle competition. So on a cackle competition, and if you've never tried entering a cackle competition, it's really a fantastic learning experience to try it. You'll find that you can download the training data, which has labels, and then you can also download the test data that doesn't have labels. And all you do is you calculate a column of data, your predictions for the test set, and you send them to Kaggle. And then Kaggle gives you a number, a single number, telling you your performance, P, on the test set. Right? And so both in the Kaggle competition and in real life, that's really the only thing you care about. And it's shocking to me how often I go into real world, organizations doing machine learning projects, and they don't really have a test set. Like nobody actually did that thing where, like, if I was a manager and my team was like building a model, I would make sure that I grabbed a few thousand data points and stored them, in a cabinet, and they don't get to look at it until it's finished. Right? It's like it's such a simple thing to do, but it's so helpful for everybody. So we're going to be talking about how we can actually, in fact, this whole book and everything we care about in machine learning is about only one thing, which is how do we get the performance on that test set to be better. There's lots of things in data science that are about things other than that, but in this particular, that's our focus really in just thinking about this machine learning task from this pure metric point of view. All right, so given that we're going to be training a model to try to improve some performance metric P, hopefully it goes without saying that choosing P matters a lot. And again, this is something that people get wrong all the time. They choose a performance measure P, which is, I don't know, whatever the thing they learned at stats class was, or whatever their, is the default in their library of choice, or whatever. In fact, choosing the performance measure, in fact, it makes such a difference. This insurance pricing company I had, like basically the only reason for its existence was I changed the performance measure. The performance measure for every actuarial system until then had always been the accuracy of the claims model, and I created something else instead where the performance measure was the profitability of the prices created. And it turned out that when we did that, we put it into insurance companies, they would get returns of some billions of dollars per year in addition to what they used to have, entirely because they picked the wrong performance measure. So this stuff really matters. Yeah.
Isn't the precision and recall, are they also good metrics to use instead of accuracy?
Yeah, absolutely. So in classification, you basically end up with this little kind of, if it's just a binary classification problem, you end up with like what was the actual answer? Was it true or false? What was the predicted answer? Was it true or false? And you end up with these 4 different numbers. And there's like a multitude of ways of adding, subtracting, and dividing those numbers to create all kinds of different metrics. So there's a Kaggle competition I'm playing with at the moment, which is the Planet Labs Rainforest satellite data competition. And they're measuring the performance using something called F2, which basically takes like true positives and false positives and all those things and combines them in a specific way. And interestingly, one of the things about F2 is you can actually decide how much you weight, false negatives versus false positives. And they are weighting false negatives by like 4x more. So to be successful in this Kaggle competition, you need to like really be focusing on finding everything that even might be there, even if occasionally you accidentally find things that aren't. So presumably in the case of Planet Labs, for whatever purpose they're going to use this satellite algorithm for, they want to make sure they don't miss anything. And in fact, this is really often the case, is that you really want to avoid false negatives, because like for many machine learning algorithms, the best way to roll them out is to use them in addition to a human, right? So like with the Planet Labs satellite imagery thing, let's say their final client actually is the military and they're trying to find terrorist installations, and every time they find something that's like maybe a terrorist installation, the next thing it's going to go is to go to a human to check it out, right? So in that case, you don't want any false negatives, you don't want to miss any terrorists. False positives, you don't care about much at all, because it's just, some analyst lucky at the CIA has to spend an extra couple of seconds checking it. And it turns out to be really easy to, in classification, to weight things differently, because pretty much every library in deep learning gives you the ability to choose the weight that is applied in the loss function to, the cats versus the dogs, or the, terrorists versus the rivers, or whatever. All right. So the experience. We've already kind of talked about this, unsupervised versus supervised. So, so a data set is just a bunch of examples or data points. And so, for example, in scikit-learn, which hopefully all of you are playing with, because it's a super easy and convenient way to understand machine learning, and furthermore, it has heaps and heaps of really well-described tutorial examples. sklearn has lots of interesting data sets, and one of them is the ARIS data. Oops, the ARIS data. I just pressed that button. The ARIS data set, which you see all over the place. It's 150 measurements of different types of iris plants, and the features of different things that are measured. And your job is to figure out which species each plant belongs to. So here we've got the target, which is what species of iris, and the features, which is the length and width of the petals and sepals. And so it's fun and helpful, I think, to try out lots of different data sets, and sklearn makes it really easy. And this is an example of supervised learning. Okay. I think what we might do is have a little break before we talk about unsupervised learning. So shall we have a little break and come back at 7:40?
What is happening with it?
I don't know. I could try image size. Hi.
Sorry, showing.
Yeah, I bought this 3 or 4 weeks ago. So.
Just 3 or 4 weeks ago.
Yeah, I really was hesitant to. I had this whole MacBook
No, I find it useless. I didn't really want it, but I wanted to get it out. Yeah. No, it's just and I prefer the physical one.
I only took the book with Jeremy.
Yeah.
So the
It's
class
not actually
gave us maybe we met somewhere else.
Place, made a few friends with them. I used to be a machine learning researcher, so they did like, you
About the eye.
It's not the same dataset.
But yeah. Yeah, I'm not too impressed. I think like a lot of the products are just lower quality.
Okay, well, hey, did you ever book?
It's the latest.
So we're just going through the book, and we're meeting every Monday.
It's very nice features.
So we are in chapter 5. And we're gonna go to chapter 11 because everything after chapter 11 is more like if you're getting CS degree and you are PhD level and you need those like deeper techniques. So I think like till the end of July, maybe beginning of August. It is so all the videos from all the previous meetings are online, so you can follow. It gets a little hairy, like it's very messy. And actually, I will definitely ask Jeremy to like talk a little bit about his book. So the deep learning classes that he was teaching here, it's 14 sessions altogether. So they were like 7 and 7, part 1, part 2, and they're a lot more like practical. So this stuff is like very theoretical in a sense, but actually today's lecture is very nice and easy. I feel like the pace is really good. Are you listen to implement stuff yourself?
I'm to research very large data sets. We have a lot of it because or use pattern detection. There's so much like you're left double.
Yeah.
Google is doing this double in the
For the diabetes, right? They were like
diabetes
You never told me, dude. Okay. Right. Yeah.
And if the right thing to do is
there's like a lot of people who, first of all, I don't know, like if you want to like teach yourself how to do things, if you get to take
right.
Yeah.
No,
Okay. Yeah. Well,
that's what
definitely.
matters.
Yeah.
Whatever works.
Yeah. Yeah.
Yeah.
That's not going to be so I know what they're saying, and I can see it, and so I can bring it to
Right. Everything's right. It's just very high. So it's very high.
projects. I exposed it to 2,000 patients. It's not small things.
Let's see. Well, first of all, you're obviously if you want to make an announcement, if you're looking for collaborators. Yeah, okay.
Not too late. It's too early.
Also,
I'd like to get your information.
Yeah, absolutely.
It's too early yet because we have to first figure out.
And I can definitely put you in touch with a lot of people. Like, and coming here, you can put yourself in touch with people like Jeremy who did some stuff in medical research too. Yeah, we have two Googlers and one person from OpenAI coming in. So maybe
At some point we'll be but first for now I need to understand the demo. You have a couple of Googlers.
So we have two presenters from Google coming in, Google Brain.
They've already been here. Should I miss them?
I didn't.
Are there any more?
So yeah, I'm sure like I'll be able to pull some more people. So it's every week we're trying to get a new person coming in. OpenAI is like really huge.
The people you had in Google, they were working on medical
No. So
Okay.
I think it's global research is really huge. It's gotten to be like this really huge organization. It used to be like 20 people, but now it's so many, and there's a big variety of what they focus on. A lot are like robotics, but a lot of stuff are like can be translated. I think. I assume you're dealing with images a lot, so
I don't think I'm gonna. I didn't think I was gonna get through your 6 sections. I don't think I'm gonna get through.
that's okay.
For a second, I got excited. You talked about the iris data set, and that's not why I was interested.
Yeah.
I'm an iris.
Oh, okay.
The
Yeah,
American
it's-
Academy lost an all poll that had more than 20 million.
Oh. Oh,
So
great.
that's called the iris data set.
Oh, great. No, well, the only thing I know about eye stuff is I bet it goes Yeah, they did it actually later than everybody else. Yeah, but the Kaggle winners.
Cool, I'm a first
The
year.
Kaggle winners. There was an international competition for yeah, please do. There was one guy called Ben Graham in the University of Oregon who was the best, but he's not famous. Ben Graham. If you go to Kaggle, we're really interested in finding like difficult business problems and data sets to help, so we can help you with this. Okay. Well, let me give you my email address.
So for a second you said iris data set. Wait, he's worked on it and now it's
Yeah. Okay.
well, thank you.
I was thinking maybe it's my like devices.
I don't really know what I'm doing here.
Well, no, it's interesting because, you know, like you, I don't have a background in mathematics. I mean, yes, I've got calculus, but I'm not. I wasn't trained as a mathematician or as a computer scientist. So I think so it's good to hear, because I think you're exactly right on about the understanding the notation, right? Because I knew that I was struggling at first to get the notation, and once you really get beyond the
Well, in our course, we don't use it.
yeah. What's your course?
Course.class.ai.
Okay, I get it. Okay, I'll go check
Like,
that out.
because like notation is really representative.
Yeah.
It doesn't really code.
Right. Right. Yeah. Okay. Well, thanks.
It's just when they do like it's like if you kind of motion that, you right next to it. If you translate it,
Okay, welcome back. So before we continue, there was a couple of really interesting questions that I thought we should, talk about more widely. So yeah, hit me with your questions, and let's read the first one as well. Yeah, because I thought it was important.
So the first question was, what is a feature basically? What can be a feature? Can anything be represented as a feature? Is anything that is represented as a number not be a feature?
Yeah. So So what's a feature? Or originally your question was kind of like, can everything be a feature as long as it's represented as a real? The answer certainly is yes. And often there's a challenge in figuring out how to turn something into a feature. And for a long time, people have been particularly perplexed by what we call a high cardinality categorical variable. So the cardinality of a categorical variable simply means how many discrete things can it have, how many levels does it have. So an example of a high cardinality categorical variable would be postcode. And there's lots of examples and ideas and thoughts on the internet about how to handle this, but nearly none of them are the correct answer. It turns out the correct answer, and by correct I mean the thing that wins the competitions, and this is like so people compete against each other globally to find the best answer. Turns out to be something called embeddings. And so we talk about word-to-vec. Word-to-vec are just embeddings for words. They're vectors represent words. It turns out you can just as easily create embeddings for postcodes or embeddings for product categories and so forth. So, and that's one of the things we handle in part 2 of the course, is talking about other kinds of embeddings. So other than that, a lot of things are pretty easy to turn into numbers. One interesting trick, though, is because CNNs, convolutional neural networks, are so mature, one trick that people often use is to turn things into pictures, right? So I know people who sometimes have to analyze like sound waves, and they'll literally like create the spectrogram as a picture, and they'll feed the picture to a CNN. And so like there are some cool tricks like that. It's not necessary to do it that way. You can use 1D CNNs, but sometimes like coming up with the simplest possible way to do something and seeing if it works is a good approach. And my student who got this patent on fraud detection actually did exactly that. He took mouse movements and he turned it into a picture by basically changing the acceleration and speed of the mouse into a different color and drawing it on the screen, turned that into a convnet, and it turned out to work really well. All right. Oh, you had a second question.
Yeah, my second question is basically on the other side of that. So that question was about features. Now, what about the target? So in one of the classification sections, you said that you could have a probability distribution over the classes to be your target. How is that different than regression or density estimation?
So what's the difference between probability distribution over classes versus a regression? And so I should explain it's not that the target is a probability distribution over classes. The target is a class. So it's a dog or a cat or a swan or an elephant. But your model F creates a probability distribution over classes. So it's like 80% confident it's a dog, 10% that it's a cat, 5% that it's a swan. And so that's what most neural nets, for example, spit out, and so then you turn that into a specific class by just doing an argmax, in other words, finding the highest number and is the index of that. Yeah, I can't think offhand really of examples where the probability distribution is the dependent variable. It's the thing you calculate. Did anybody else have any questions about stuff we've covered so far? Yeah.
I had a quick one about a comment you made. So you said in the first half of the class you just used laptops, and in the second half you used a box, actually.
The first half we used AWS
AWS,
instances.
Yeah, is there a reason why AWS is not sufficient for doing all these things? Like
It's totally sufficient. It's just that I just told people in the class, like, given that you've now spent 70 hours studying deep learning and you've come back for more, you probably like it, and so you probably don't want to keep spending 90 cents an hour for something which is less than half of the speed of something you could buy once off for $600.
Yep.
You know, so it's just an efficiency thing. The GPUs on Amazon instances are very underpowered and very expensive. They're kind of 3 generations out of date, 2 generations out of date. All right. So unsupervised learning algorithms, this is really a similar description of like the kind of the probability mass estimators we talked about before, although there's quite a few things you can do with unsupervised learning algorithms. So unsupervised learning simply means we don't have a label, so we don't know whether it's a dog or a cat or whatever. And so I've got a kind of visceral reaction to anybody who claims to have an unsupervised learning problem, because an unsupervised learning problem implies you don't have a problem to solve. If you don't have a problem to solve, why don't you go and work on something which is a problem? Like what the hell are you doing? So where this comes up is often that people basically have like some unstructured data they want to create like features for that they want to use then for something else. So like people in marketing very often might do clustering, and they're basically doing clustering so that then they can like target campaigns better, for instance. But here's the thing, anytime you think you have an unsupervised problem, you can probably turn it into a supervised problem by coming up with a problem to solve. Like the Word2Vec example is a really good one, right? In that case, because they were trying to give the world a set of features that anybody could use without having to retrain on hundreds of millions of books, hundreds of millions of sentences from books, they were genuinely trying to not solve a specific problem, but the way they did that was to kind of come up with a problem that if they solved it was likely to create features that were likely to be useful for lots of people. So the reason that unsupervised learning of itself is generally not so helpful is because by not telling it any problem at all that you want to solve, it has no way of knowing which features are more important. So I'll give an example. And in fact, in deep learning, the way we do unsupervised learning is always to invent a supervised learning problem, right? And so in images, for example, the thing we invent is something called autoencoding. And so an autoencoder is something that literally takes a photo as input, sticks it through a neural net, and the output is meant to be the same photo you started with. And the reason it's not easy is because in the middle of the neural net, you have less activations than you have pixels to start with. So it basically has to compress it and decompress it. And so these autoencoders, you still see people recommend them all the time, you see them everywhere, but here's the thing. Because it's caring about every single pixel equally, it's going to care just as much about what color the sky is, what do the shadows look like, stuff like that, and they're probably things you don't care about. Right? So if instead you could come up with some kind of more meaningful thing, so an example of a more meaningful unsupervised problem people often do instead is something called Siamese networks, where they feed in pairs of images along with a label saying 1 or 0, are these two images pictures of the same thing or of different things? And so that's way more helpful in terms of the features it creates because it has to actually understand which pixels are important in recognizing what thing it is. And it has to learn to be not care about lighting conditions and so forth. So, yeah.
When you're looking at autonomous vehicles or transportation features, there's just so many different types of features. Wouldn't that be a case of unsupervised?
No, because all we're talking about here is the label, not the features, right? So deep learning is great at handling lots of features. And so in this case, for autonomous driving, let's say you're dealing with whether it be the LiDAR or the cameras or whatever, most commonly what you're trying to do is know what the things are. So your labels generally will be segmentation pictures. That's a tree, that's a person, that's the line on the road, and so forth. So that's always handled already with supervised learning. Yeah, so supervised versus unsupervised is only about the targets or the labels, not about the features. And so generally speaking, you just try to remember that in practice, particularly when they use deep learning for unsupervised learning, you'll always see that they turn it into a supervised learning problem. People almost never talk about it that way, but that's always what they do. Okay. As it mentions here then, often the lines between unsupervised and supervised learning are blurred. They give a couple of specific mathematical examples of how you can actually turn supervised into unsupervised and vice versa. They're never used in practice, so you can happily ignore them. Okay, so one which I think is awesome is semi-supervised learning. So remember I mentioned the difference is only in the labels that you have, and maybe you have a data set where you don't know which ones are cats and which ones are dogs, but you know that they are pictures of cats and dogs. What do you do? Okay? And the answer is you label them. Right? But if there's a million of them, you probably don't want to label all a million. Right? So what you do actually is you label 100 of them. Right? And now we have something called a semi-supervised learning problem. Semi-supervised learning means you have labels for some of them. Right? And it turns out that there are some pretty handy techniques for semi-supervised learning. The really dumb, simple approach is to create an autoencoder on all of the data and then use those features to start off your neural net with 100. But then there are better ways you can do. And perhaps most interestingly is there's something called active learning, which is where you label 100, you build a model using some approach, and then you use that model to tell you of the remaining 900,000, which ones should you label next, which ones would be the most informative. And it turns out if you use active learning, then you can require exponentially less data to be labeled. So that's really a handy approach. No, so active learning is a trick for semi-supervised learning. So semi-supervised learning simply means more than 0 and less than 100% of your data points are labeled. And active learning means the labeling process itself is in some way controlled or directed, so that picking which things to label next is done with the help of some kind of model or algorithm. Yeah.
You would still have a human do the labeling.
Exactly, probably a human or something. So yeah, like often that's how data sets are labeled with like Mechanical Turk or something. You decide which ones to label next and send it off to Mechanical Turk, and it sends back a few more. We certainly found that really helpful in medical stuff. Like radiologists are really expensive. You don't want them to label 100,000 X-rays. So you figure out which X-rays to get them to label, which ones are you least confident about. Is normally the way you do it. Yeah.
What would something like matrix factorization that people use for recommendations come under? Because you don't necessarily have a target and then.
Well, actually you do. And so this is actually lesson 4 of our course. So you can actually do matrix factorization with a deep learning library. Basically, your target is the actual recommendations people had, and your weights or your parameters are the presumably truncated matrices you're trying to multiply together, and your loss function is then whatever mean squared error or something. And so there's actually a whole area called probabilistic matrix factorization, which really became popular thanks to the Netflix prize, which is all kind of based on this idea. And it's really fun. It turns out that instead of doing a matrix factorization, rather than just going this matrix times this matrix, you can actually feed the two matrices not just into a dot product, but into a small little neural net. And you only change 2 lines of code to do that, and you can often get really way better answers. So yeah, it's a really interesting area. Okay, so there's a whole field called reinforcement learning that's pretty interesting and pretty controversial. Take, for example, you want to create something that can play the Atari game Pong, right? And so your inputs are, at each time point, are you pressing up or are you pressing down, right, to move your panel? Your target, though, you don't have a label for each time you press up or down. You don't get a label until later when finally either you win that round of Pong or you don't, that particular exchange. So this is what they mean by interacting with an environment, right? The reinforcement learning algorithm is playing Pong. And the key problem here is what we call credit assignment, which is basically to say that your label is delayed. Like I should have pressed down here, but actually I pressed up. But it's really like quite a few frames later that you lose as a result. It turns out you can still use deep learning for this. And basically the trick is to create like a pretty standard data set where you take that label and you kind of paste it into all of the things that eventually led to it. It's really, really slow, and it may well turn out that it's, a lot of people think it's not the right way to solve these kinds of problems, but for many problems it's the best, or one of the best we have for now. So a lot of people ask me, can I add reinforcement learning to the course? And so far I haven't, because I'm not convinced it's here to stay, and I only like to teach people stuff that's here to stay. It might be, but for example, genetic algorithms seem like they may well be better. For instance, yeah.
How did something like AlphaGo get around not having to use reinforcement learning?
Yeah, great question. So AlphaGo is an awesome example of an end-to-end system that I really love talking about. The first, okay, so AlphaGo is the thing that played and won Go, and most recently beat the world champion. Apparently, it's like only 19 years old, which is crazy. So I'm more than twice as old as him, and I can't play Go that well. The interesting thing about Go is that there's a lot of different moves you can make at each point, which means that there's this combinatorial explosion of possible things like three plays down the road. So with chess, a fast enough computer can look at what's every possible next step, just about, and go to the end and find out which one ends up winning. With Go, you can't. Like even if every atom in the universe was a microprocessor, I think you still can't. So what you want to do is you basically want to build a little tree of like a few moves ahead, and then see of those moves ahead, that final board that could happen, like how good is that board? And unfortunately in Go, there is no way to say like this board is better than that board. But a human expert could look at them and immediately go, that's in a good position, the left-hand side is very strong, there's a nice defense here, you know. But they can only do it in these kind of intuitive, vague ways. So here's what they did. They created a ConvNet. And the ConvNet took as input pictures of boards, basically, or board layouts, along with a label saying, did that end up winning or not? And that way, they ended up with basically something saying, you could now give it a board and get back a probability of winning. And that was a score, right? So they basically did this tree search. They did it stochastically, actually, something called Monte Carlo tree search, but basically a tree search. And with those, as many boards as they could get to, they then used a ConvNet to say, what's the probability of winning from here, just by looking at it and getting a feel. So, yeah.
Is that a general way around reinforcement learning, where you pick a next move and then snapshot it and say what's the likelihood this ended up?
That's basically actually what I described before as reinforcement learning. If you think about it, kind of what happened was we ended up taking the final label and copying it into all of the previous states. So that kind of approach is called policy gradient. It's a pretty simple approach that seems to work just about as well as anything else. Andre Karpathy has a really great blog post, actually. So if you're interested, you can look up Pathy. I can't remember if this is R or not. Pathy? Reinforcement learning. His convolutional neural networks course, by the way, the Stanford CNN course is really great as well. All right, so reinforcement learning, definitely fun, may or may not be pointless. All right, so here's an important piece of nomenclature, a design matrix. Okay, so when you see design matrix, it simply means all of the examples stacked on top of each other as rows, right? And so in practice, everything you do pretty much is going to be, you're going to have a design matrix of your features or of your input data. So each row is an example, each column is a feature. Iris has 150 examples with 4 features. Here's some important notation. So this represents a 150 by 4 dimensional space. So this R150 x 4 means 150 rows and 4 columns in a matrix. And they're generally indexed like this, right? So at this point, you notice that X isn't bold anymore. So that means it's a single number. And I refers to which row, in this case it's which plant. And then the next bit, which is the 1 here, is which feature number are we looking at. Okay, so rows by columns. So I always forget which way around it is, and like eventually my wife told me the song they learned when she was doing her PhD, which is Roads by Collins, Roads by Collins. So anytime you forget, you say Roads by Collins, Roads by Collins, and you got it. Okay. Yeah, so here's something important. And this is like, if you haven't done much deep learning, you'll be surprised at how incredibly primitive we are with this. Every vector has to be the same size. And so literally, the big ImageNet competition, every image is turned into a 224 by 224 downsampled image. It's a huge problem, and we don't really have a solution to it. I'm not just going to say, just suck it up. Like, don't. Like, this isn't okay. There's got to be better ways to do this, but just be aware that that is kind of where we're at. Yeah.
What about recurrent neural nets? They are kind of designed to handle different.
Yes and no. So recurrent neural nets can handle arbitrary length sequences containing a certain number of time steps. But at each time step, the representation still is of a fixed size. And even then, most libraries still require you to feed in a fixed size vector, even into the RNN. Not all of them, but still most. There are things called dynamic RNNs, which are starting to get around that. But if you use, say, Keras to build an RNN of like a sentence, then your input has to be always the same length. So there's a function in Keras called pad sequences, and you pass into it your vector and some length. And it basically, if your vector is longer than that length, it'll truncate it, and if it's shorter than that length, it adds zeros to it. Like this is like something you'll do every time. Yeah, it's a bit of a bummer that with vision, for example, we end up kind of reducing the size of everything to the lowest common denominator. That's kind of where we're at. There are people trying to fix this problem, but probably not as many as there should be.
Before we leave recurrent neural net, is that what you use for time series data in general, or what do you? Okay.
No, there's actually some people who think that RNNs are a temporary blip that will disappear. For pretty much everything that people are using RNNs for, it turns out that CNNs are even better. So like literally even like language translation, the state of the art currently is a CNN. So I always tell people to start with a CNN, particularly the time series. You can, something that's just super cool is that you can create a CNN with like multiple different filter sizes, right? So like if you're doing language, it could be like 3 characters, 5 characters, 7 characters. And then you can concatenate them all together. And so you can have this kind of like multi-period CNN. They work really well with the time series. And then like at the end of that, you can always chuck the final results of those convolutional layers into an RNN, right? So you can do CNN into RNN. That works really well. So yeah, I would always start with a CNN. They're easier to train, they're faster, they're normally the state of the art. Yeah, okay, so as well as our design matrix, we then have also a vector of our labels. And so generally speaking, a numeric code, if it's a classification. And then in practice, we always turn those numeric codes into something called a one-hot encoded matrix, which basically means if you have the numbers from 0 to 3, then basically 0 gets turned into, let's write it down, 1, 2, 3, gets turned into 1, 0, 0, 0, 1 gets turned into 0, 1, 0, 0, 2 gets turned into 0, 0, 1, 0, and 3 gets turned into 0, 0, 0, 1. And so that's a one-hot encoded matrix. So that's generally what we do in practice. One thing to note is that what we always do with matrices in deep learning is that we multiply them by other matrices. The result of multiplying a one-hot encoded matrix by another matrix, if you think about it, is like, so here's our other matrix. Is like, let's say at this row, we have this row, 1, 0, 0, 0. So we're going to go 1, then take that, and then no, 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 right? And so if you multiply that by this matrix, you're going to end up just taking the first row. Whereas if you multiply this, you'll get the second row, this is the third row. And so anytime you've got a one-hot encoded matrix times another matrix, you can actually always replace it with just an indexed lookup by row. And so this is important to remember, because this often is going to be a difference of hundreds of thousands of times in terms of speed and memory. Most neural net libraries have a way to kind of tell it that you really just want to do an index lookup in this way. And in fact, really nice libraries like PyTorch, this is like the default. It's that you use a single integer and it does lookups for you. But behind the scenes, it's basically, you can think of it as doing a one-hot encoding. Okay. One thing they don't mention here is like multi-label classification. So maybe we'll just mention that as well. So this planet competition where you have to take a satellite image and say what it's an image of. They actually give you a list of things. They say there's agriculture and roads and a river in it. So they'll have like 3 labels. So that's just another type of model, I guess, is where you have multiple possible labels. They're not really any different in terms of how you deal with them, but you have different activation functions and loss functions that you can use for those. So here's like a way just to kind of practice the notation, I guess. So with linear regression, our input is a vector, because it's bold. There are n things in it, because it says Rn. We're predicting a scalar, because it's not bold, and we can also see R doesn't have an n on it. So it's going to take a bunch of numbers and turn it into a single number, which is a linear function of the input. So you'll see here, y hat is the value our model predicts. This is like totally standard, right? If you see something hat, it should mean this is the thing that you're predicting. So that's really important to remember. So given that our actual value is y, the thing we're predicting is, our guess is y hat, right? So what's y hat equal to? It's equal to the transpose of the vector w by the vector x. So it's some bunch of weights times something. You could also write this just as x times w, right? But like you can turn them upside down and add the transpose, gives you the same thing. It just depends whether you want to think about your final result as a column or a row. So anytime you kind of see something written like something transpose something, just remember it's the same as basically turning it around and you end up with a column instead of a row. So your W are your parameters, and the reason we write it normally as W is because we also call them weights. So one thing is, if you haven't done much linear algebra, often you'll see things written in ways that are a little unfamiliar because like you will have previously been used to seeing them written as sums, right? And so for a while, it's a really good idea if you see something written in a linear algebra form and that doesn't feel natural to you, then just like write it out as a sum. In fact, even like my wife, who actually is a math PhD and actually is teaching graduate level numerical linear algebra, most of the time when I ask her to like figure out some linear algebra equation for me, she writes out the whole thing with sums. So like even people who know what they're doing seem to find this useful. All right, so we end up with a bunch of weights, and so you're going to basically end up with, this is important to notice, is that W is a vector, or else X is a matrix. So you've got one weight for each feature. So now that we're indexing into them, they're not bold anymore, right? So we've got a particular feature, has a particular weight. And if it's a positive weight, then we're saying, okay, if that feature is higher, then our final answer is higher. Negative weight is the opposite. More importantly, perhaps, is the magnitude, right? So if the absolute value of the weight is higher, we're getting more of it. And this is a really important way to think about matrix products, is that you can basically think of this as telling you the weights of a linear combination of all of the columns in your matrix. So generally speaking, when you learn linear algebra, you tend to learn it as being more like an element-wise by element. You go along this row, you go down this column. But in data science, it's much more convenient to think of it as something where you actually grab a column at a time and combine them together with a different weight for each column. And if this isn't something that feels supernatural to you, there's a really, really, really awesome thing which you should watch even if it is natural because it's just so cool, called 3 Blue 1 Brown, which is basically this guy who is really good at linear algebra and really good at teaching and really good at animation, and he's written his own animation library to create this series of films showing you like how linear algebra works in a totally intuitive way. He does it actually for all kinds of areas of math, but his linear algebra sequence is great. He doesn't make any money unless you sponsor him on Patreon. So if you do like them, be sure to send him some money. Yeah. So if you're like me and you don't really have much of a background in linear algebra, it's great to use resources like this to get to the point that it feels, you kind of have a sense for it in the same way you might have a sense for regular algebra. Okay, so most interestingly, if a feature's weight is 0, then in our linear combination of columns, it's not going to be a part of it at all, right? So that's all that happens. One of the reasons that getting a great feel for linear regression is important is because deep learning is just a series of linear regressions with simple little nonlinear activations in the middle. And in fact, normally the simple nonlinear activation is replace the negatives with zeros. So it's basically do a linear regression, replace the negatives with zeros, do it again, do it again, do it again, and that's a deep neural network. Right? So you want to make sure you feel super comfortable with linear regression. Okay, so then we've got this different design matrix that we're not going to use for training. Okay, so that's our test set. It's going to evaluate how well the model performs. And we do know, or at least somebody who's going to test us out knows the true targets, even though we didn't use them for training. So we can now use this to compute performance. And a very common way to compute performance is to use the mean squared error. Okay, so the mean squared error is, as you can see, it's quite simply just whatever your predictions are minus whatever your actuals are, right? Because we've got the hat here. Okay, and then we can square them for each row, okay, and add them up together, and then we can just take the average. Okay, so that's mean squared error. When they're the same, that'll end up being 0. So here's some notation you definitely want to be comfortable with, which is these little bars. This is called the norm, and a norm is simply something which starts with a matrix and turns it into a scalar. And in some way it tells you something about like the size of that matrix or something like that. And there's quite a few different kinds of norm, and which kind of norm it is specified by the symbol here. So this is called the L2 norm, and the L2 norm literally is equal to the sum of the squares. Well, actually, the square root of the sum of the squares, right? Sorry, that's it, matrices. It applies to matrices and vectors. In this case, we've got vectors. So the L2 norm here simply says take the difference of the vectors and take the roots of the squares, right? And you'll notice that this thing didn't have a square root, So that's why we then square it again. Right? So this is just literally two ways of writing the same thing. And the reason this is important is you'll find both in this book and in lots of papers and stuff, people generally use this notation much more often than this notation. So you want to make sure you know anytime I see the double bars, it's a norm, and the thing on the bottom tells me which norm, and then this here tells me that I'm squaring it. That's only notation. There's nothing.
What is the, in the one above it, does it mean the same thing, the I in the formula that's higher, right there?
Yeah, what are you asking? Oh, this one here?
Yeah, no, does it have the same context as the two below, you know?
Okay, so what we've got here is y hat minus y is a vector minus a vector. So that means that this is a vector. And so when you've got a vector, the thing here generally means the index, right? So like if it's like an array in a programming language, you'd put it in square brackets. So this is saying the ith element of the vector y hat minus y. So if this was in NumPy, you would have written y hat minus y square bracket I, right? And then in this case, and then we're taking the power of 2, so it'd be like np.val, all that.
It's basically going and operating on the index value.
Yeah, we're grabbing one of them, and that's why then we can sum it up, right? And like something, if so like you and I haven't got such a math background, I know because you told me at the break. So for you and I, what we should do when we see something like this is we should try and write it in NumPy, whatever language we use. So you just go ahead and you kind of go, okay, so this is like np.pal y hat minus y, whoopsie daisy, y hat minus y, comma, 2 dot sum. Okay. So
The 2, by the way, when you have 2 down the norm, it means it's a Euclidean norm. You can have a bunch of other norms. Okay. It just means it's
yeah, the L2 norm.
Yeah. Okay.
In fact, the general, I can tell you that as well. So in general, if you've got something, put here, P, something that looks like that, it means the sum of xi to the power of p, and then the pth root. Okay. The one you'll see a lot of is the L1 norm, which is just the same as the sum of the absolute values. All right, so in this case in linear regression, obviously we're trying to find the weights which give us the smallest MSE. And so you want to be very familiar with gradients and derivatives when you're doing deep learning. You don't need to know heaps about them, but one thing we do need to know is that when you have your optimum, your gradient is going to be 0. Okay, so therefore we can say the derivative with respect to the weights of our loss function is 0, and we can solve for that. So we just replace the MSE with the actual equation we had. We do some algebraic manipulation, and we end up with this. Now this thing of x by xt by x inverse xt y, you see a lot. You don't see it so much in deep learning because it's like this is an analytical solution to the linear regression problem, but it's worth kind of being able to recognize that because like it often pops up in papers. And anytime you see it in a paper, you can just replace it in your head with analytical solution of the linear regression problem. In practice, by the way, you never actually solve it this way because matrix inverses are costly. And so for those of you who have been here in prior sessions might remember the singular value decomposition. That's actually how we generally calculate these in practice. Yeah, so here's a picture of linear regression with a single predictor. So you end up with just a line, and as you change the weight in your linear regression, because it's a mean squared error, you end up with a parabola. So this is really important. This particular line doesn't go through, or does it? Or maybe it does go through 0. Oh, okay. In general, we don't necessarily want our lines to go through 0. So people will often write this, where they basically just add this plus b, which allows us to move the line up and down. However, in nearly all papers and books, you'll basically never see anybody write that plus b, or hardly ever. And the reason why is that we just basically assume that there's a column of all ones that's been added to our x, right? So if you add a column of all ones to your x, then you don't need to add the plus b anymore, right? You can basically add this is called a bias in that way. Now, even though in like the math papers and books, you never see them, or hardly ever see them worry about the bias, you just assume that there's this column of ones there. When you do it in practice on a computer, you don't actually want to add a column of ones because it's a pain in the ass. So you'll find that like all the libraries do explicitly say like, do you want bias or not, will be one of the parameters, and there'll be like a dot bias property that you can get and stuff like that. So there's a difference between the kind of programmer's way of thinking about this, which is, yeah, there's a thing called bias, versus the mathematician's version of this, which is like, we can ignore it without loss of generality. You'll see the word affine all the time. Affine just means linear with a bias, right? And so the kind of real definition of a multi-layer perceptron is a bunch of affine transformations with nonlinear activations between them, right? So, and so I tend to tell people, to understand deep learning, you don't actually need to understand linear algebra, which is a huge field with lots of stuff you don't need. You just need to understand affine functions. Okay. So the ability to take your training results and have it work well on unseen test data is called generalization. And when it works well on the training set but not well on the test set, we would call that generalization error or test error. Okay, so clearly this is the thing that we just minimized on our mean squared error of our training set, but the thing we actually care about is the test error. So why is that any use at all? And the reason it's useful is because we start with an assumption. We assume that the training set and the test set are what we call IID, independent identically distributed data sets. Or in other words, we assume that the two data sets are both come from the same probability generating function. In other words, they come from the same kind of causal source, if you like. And if that's the case, if that really is the case, and you minimize your training error, you'll get something that also minimizes your test error. There's a whole bunch of stuff about statistical learning theory here. And particularly they talk quite a bit about stuff like VC dimensions and so forth. I've never found any of that stuff remotely useful in practice. So it does seem if you want to get papers published, you need to like talk a lot about this stuff because professors really care about it. But the actual practice of creating good machine learning models, you never worry about this like mathematical purity. You just worry about these two things, which is I want my training error to be small, and I want the gap between training and test error to be small. So the reason that the gap between training and test error isn't small is because what we actually did was that we chose parameters that reduce training set error. And so that only means that our expected test error is greater than or equal to the training error. And so what can happen is in particular, we can end up with something called overfitting, which means that this gap isn't small, or we can end up with underfitting, which means that this gap isn't small. So underfitting basically occurs because we used a model which was like not complex enough. It didn't have enough degrees of freedom. Or else the reason that we have overfitting is generally because we had a model that was too complex. It had so many degrees of freedom that we ended up fitting the training set rather than the underlying generating function. So they've got a picture of this. Here we are. So here's an example of some data points, right? And so here's underfitting, which is I just fitted it with a linear regression. And here's doing a good job, which in the word is capacity, appropriate capacity. So we've fitted it with a quadratic. And here's a bad job, which is fitting it with a 9th degree polynomial. So you can see why overfitting is bad, because you end up with like values that just clearly aren't going to make sense. Incidentally, how did they create this 9th degree polynomial? Well, it turns out that if you add additional, squares or other powers as columns to your data set, you can just add that to the design matrix and still solve it with a linear regression, right? So what they're pointing out here is basically that you can create a 9th degree polynomial first, make that your design matrix, and then use standard linear regression. So this is called feature engineering or feature creation. You can create additional features and still use linear regression, right? So that's how they did this 9th degree polynomial. So the point here is that this degree 9 predictor could represent the correct function, but it can also represent functions like this that fit exactly and aren't the correct function. What we want to do is try and change the capacity. So one way to do that is to just reduce the number of features that we add, or try to reduce the representational capacity of the model, which is basically what that means. Or kind of change the functional form that we're using so it has less parameters. This is all this stuff about the VC dimension, which I'm going to skip over. One interesting example they talk about is we could go as far as creating a non-parametric model, which generally in practice means something called nearest neighbors. It's a really great model, actually. It's basically to say, let's not build a model at all, but like save all of the original training data, and then there's some new data point that comes in. Let's see which original training data points it's closest to, and we're just going to assume that the average label of those data points is our prediction. And it actually turns out that that is a extremely good baseline a lot of the time, right? So anytime you're trying to create some fancy model, it's always worth chucking the nearest neighbors in there as well to see if it works well. So that's kind of your highest capacity version. And so just before I wrap up, we'll finish this section. Here's another good place to look at notation. And I particularly want to point out this argmin here. You're going to see this all the time. And so make sure you feel comfortable with it. So what we're doing here is we're saying, in fact, there's so much notation of interest here. We're starting out with a matrix X, okay? And remember, rows by columns, so I, the ith row, okay? And colon means the whole column, right? So therefore, this whole thing means the ith column of X. So that's a vector. And then we're going to subtract our test vector, little x. And then we're going to take the L2 norm, the Euclidean norm, squared, right? And so then we try that this is the row, the ith row. We're going to try that for all of the rows, so for all of the data points, and we will select the one where I is the smallest, right? So this whole thing here, therefore, refers to the nearest neighbor, right? And so it's quite good when you try to get familiar with the notation is when you already know what something is, see how the notation describes it.
Jerry, just to,
Yeah.
I think you just got that slightly wrong. Just like the one where the norm is the smallest, the I, which
Yeah, sorry, that's what I was trying to say. Sorry if I said something different. Thank you for making sure that was clear. Yeah, yeah. So, and in fact, I think there's meant to be like an I here, like you're meant to kind of say which thing are you doing this over, although I guess there's only one parameter here, so I guess it's kind of clear. So obviously it's like argmin, so like find the minimum value of I such that that function is minimized. Thank you very much. So, yeah, okay. Just the only thing I do want to mention before we finish is this section called the no free lunch theorem. You could ignore it, and anybody who ever says the word no free lunch theorem, you could ignore everything they say after that. What it literally, and that's basically what Goodfellow and Joshua Ventura say here, but they're not as rude about it. I'm Australian, so I don't have to be polite. What this says, the no free lunch theorem says, is that there's no model that works well for every possible data set. But the important thing to note is that there's no data set we look at which is like in any way representative of every possible data set. We look at data sets that like make sense. You know, they have like relationships and structures. So as they point out here, in real world applications, there are algorithms that work really well for all the actual things that people actually use. And basically those algorithms are ensembles of decision trees, which means random forests and GBMs, and deep learning. You know, if you haven't done a lot of machine learning before and you're thinking like, how am I going to learn all these things? Don't learn all the things. Learn the two things that actually are useful. Okay. All right. Thanks, guys. Sorry I didn't get too much.
Thank you so much. It's such a treat.
Thank you. Wow, I got through even less than I thought.
But it
I just go on.
was thorough and it was good.
Thank you.